We're going to be looking at 3.2b, which is the first page of that thing that you just got. So the next part of this unit is doing KSP calculations. And I think there are, is it 4 or 5 different types? And none of them are especially difficult. What becomes tricky is once you know all of them, if I give you like a random selection of questions, using the right tools in the right context, yes? So we're just going to hit them one by one, and then we'll mix them all up together, and we'll go through like recognizing the question types, okay? So in this particular one, we are looking at taking the solubility of a compound, so that will be given to you. So the question will say the solubility is such and such moles per liter, okay? And then you will have to find the KSP. So there are, how many steps? 4 steps. This is the short one. You are going to write the SEE, the solubility equilibrium equation. That's step number 1. And you'll notice I've put marks along the side. These are what I could typically give you in a free response question. So if you don't write that, you would be losing half a mark. Okay, so make sure you do that. Second thing, KSP expression. Again, that's worth half a mark. You will find the ion concentrations. Most of the time, this is going to be proportional to the coefficients, okay? Because these are all going to be like a dump and stir type situation where you dump in the compound of interest and you stir it. So if it has a 1-to-2 ratio, you will have a 1-to-2 ratio. And then finally, you plug it into the KSP and solve. Steps 1, 2, and 3 can be done in any order that you want to. You can find the ion concentrations first. You can do the order doesn't matter, but what I'm going to recommend is that you do these 2 first because they are going to be something that you do in common in all the problem types. And you can get 1 mark on your question just for doing that, even if you can't figure out anything else about it. So, you know, if you get a question where you're like, I don't even know where to start on this one, yes, you do know where to start. Write the solubility equilibrium and write the KSP. And you've got at least 1 mark out of like 3 or 4. So that's not bad, right? Okay. So here we go. The solubility of barium sulfate is found to be 1.05 times 10 to the minus 5 molar at 25 degrees Celsius. And we not need to calculate the KSP for barium sulfate. So how can we tell that this is a dump and stir type question rather than mix and match? How many compounds are listed here? Just 1. You can't mix and match compounds if you only have 1 compound. Does that make sense? Yeah. So we know this is dump and stir. You might be thinking, why do we care? It'll become more clear as we go through all the different problem types. Calculate the KSP. What is the first thing we're going to do? We're going to write the solubility equilibrium equation. And we're going to refer to that so often that I'm going to call it the C, the SEE. What would the solubility equilibrium equation for barium sulfate be? See if you can write it yourself. And then if you can do the next step as well. You can write the KSP. job on that because you already know how to do this, yes? So it's going to be barium sulfate solid in equilibrium with barium 2 plus aqueous plus SO4 2 minus aqueous. KSP, most people were getting this as well. KSP is the barium concentration times the sulfate concentration. Now the third thing you want to do is to find the ion concentrations in molar. Now if you did 3.2a, you were already working on finding ion concentrations, yes? So if we know that the concentration of barium sulfate is 1.05 times 10 to the minus 5 molar, then what is the concentration of barium? It's the same because it is a 1 to 1 to 1 ratio. So this will also be 1.05 times 10 to the minus 5 molar. And this one will be 1.05 times 10 to the minus 5 molar. Whoops, sorry. What do you think you will now do with those concentrations? You stick them into the KSP. Oh my gosh, 1.05 times 10 to the minus 5. And I'm putting it in twice, so I'm just going to write that I'm going to square it. And we get 1.10 times 10 to the minus 10. And then all you have to do, once again, just like when we did KEQ questions, you need to check and say, do I need units? Because some questions you'll be solving for molarity, some you'll be solving for the K value. Here we've solved for K. Do we need units? No, K does not have units. So we don't need units. What's the other thing you should check for? Sig figs. Are we good? Yep, we are. So put a box around it and you are done. Do you like that? Pretty easy, yeah? Okay. Let's try another one. Let me know if I'm scrolling up too fast. I'll give you another minute because I know some people are still writing. Okay. So our next question, we are given that a saturated solution of silver bromide contains 1.33 times 10 to the negative 4 grams per liter. Calculate the KSP for AgBr. Well, the only things that are different here, otherwise it's pretty much the same question, is that you need to recognize that the solubility is the concentration of a saturated solution. Yes? So this right here is the solubility in grams per liter, because we were told that is the concentration of the saturated solution. The other thing you need to recognize, and this is easy to miss if you're on a quiz, is that you must, in your KSP, remember KSP, we use these square brackets. What do square brackets mean? Concentration in what? Moles per liter. What that means is before we can solve for KSP, what do we need to do to our solubility? We need to convert it from grams per liter to moles per liter. So let's do that. So concentration of Ag, Br, and I'm going to put a little SAT down here for saturated, is equal to 1.33 times 10 to the minus 4 grams per liter. How are we going to convert that into moles per liter? Molar mass. And so the grams have to go on the bottom and the moles have to go on the top. And the molar mass of silver bromide is, let me see. Oh, wow, that's interesting. Okay. The answer key has something really, really wrong in there. So I'm going to just plug that into my calculator right now. No worries, I have to calculate the mass of silver bromide anyway. So 107.9 plus 79.9 is 187.8. So that is 187.8 grams per mole. And we do that 1.33 times 10 to the negative 4 divided by 187.8 equals 7.08 times 10 to the negative 7. What will we do next? We're going to do the solubility equilibrium. And we're doing that for AGBR. AGBR. Equilibrium arrow. Ag plus Br minus. Oh, and I forgot my solid there. I'm going to leave a little space underneath my solubility equilibrium equation because I'm going to want to be able to write my ion concentrations under there. It's just a nice place to write them. So I'm going to do my KSP, but I'm going to leave a little bit of room. What is our KSP equal to? Tell your partner. What would you write? So it's going to be concentration of silver times the concentration of bromide. Now, if we want to be finding KSP, what do we need? We need to use the ratio to find the ion concentrations. So all of these, and in fact, I could just write it like this. I could say the concentration of silver is the same as the concentration of bromide, which is the same as the concentration of silver bromide. So there's a number of ways of showing this work. You can write it underneath 3 times. Yeah, like we did in this last one. Right, where you just write it directly underneath. Like here. When you do that, if you've got this times 10 to the minus whatever, you need to leave a little bit more. You need to make it a bit wider though. I didn't leave myself enough room here in my next one. So I'm just going to write that they're all equal, and they are equal to that there. So that's 7.08 times 10 to the minus 7 molar. So that's our third thing that we get marks for, is somehow writing down what our concentrations are. What do we do next? Plug those in. Yeah. Concentration of silver is 7.08 times 10 to the minus 7. Concentration of bromide is 7.08 times 10 to the minus 7. And we get 5.02 times 10 to the minus 13. At this point, what should we be doing? Sig figs and check to see if we need any units. Do we need units? Yes. Yes, you could have. So you could either write it like this, or you could write it like 7.08 times 10 to the minus 7 all squared. Either of those is fine. Yes. You either need to write that, or underneath, like had you written this a little bit further apart. Whoops. You could write underneath 7.08 times 10 to the minus 7 molar, 7.08 times 10 to the minus 7 molar, 7.08 times 10 to the minus 7 molar. Okay, the reason I'm having you do it every single time, I mean, it's super simple when it's 1-to-1-to-1, but if you don't have the habit of writing it every time, you might not write it when you need to, which is when you have a not 1-to-1 ratio. Okay, yeah. Yes. I get 5.015. Because it's not 7.08, it is 7.082. Yes? So I kept my number in my calculator, even though, yeah. But because I need 3 sig figs, I would actually use at least 4 digits for my calculation. Yeah? So I think our sig figs are good, yes? Yes, and do we need a unit? No. So we're done. Do you want to try the next one yourself? Yeah, give it a go. This one has a little spin on it, so watch out for your ion concentrations. I'm going to go get water, and I'll be right back. It will give you the right answer. So for multiple choice, do that. Okay, but here you're going to need to your PSP expression and then actually show. Oh, I'm sorry. This actually should be a 2 in front of the house. In front of the AC. And there should be no 2 here. Yeah. Okay. So folks, I'm going to go over a couple of things. Yeah. Oh, I know. So I'm going to show you what you get marks for in this question, and you can grade yourself, okay? So let's see what we've got here. We have concentration of Ag2S, 3.2 times 10 to the minus 15 grams per liter times and let's see what we got. That was, oh my goodness. Sorry, I'm just trying to cheat here. 247.9. 247.9, and that gave us 1.29 times 10 to the minus 17 molar. So for that would probably be between 0.5 and 1 mark, okay, just depending on what the rest of the question is worth. So let's just say for today it's 0.5 marks, okay? Let's see what else we got. We need the solubility equilibrium equation. AgS solid gives Ag plus aqueous plus S2 minus aqueous, and I forgot to put my coefficient and my subscript here and my coefficient there. So that's going to be 0.5. If you forgot your charges, take off 0.25. If you forgot your states, take off 0.25. Okay? So states and charges. Second thing we need is we need a KSP. KSP is equal to concentration of Ag plus squared times the concentration of S2 minus, and there we are. And don't forget, once again, you still need your charges, and you need the exponent, 0.5. But take off 0.25 if you're missing any of these things, any of those places. I'm actually going to rewrite this because I did not leave myself enough room. Oops. Okay, at some point, you need to show those. That's one way of doing it, is to put them underneath the SEE. Yes? Another way of doing it would be to say, for the concentration of sulfide, the concentration of sulfide is going to be the same as the concentration of silver sulfide, yes, because it is a 1-to-1 ratio. So you could just put that there if you wanted to for sulfide. Yes? For silver, though, you would have to say concentration of silver is equal to 2 times the concentration of Ag2S, which is 2 times 1.29 times 10 to the negative 17 molar, which is 2.58 times 10 to the negative 17 molar. So that work would be worth like 1 mark. So showing your ion concentrations and how you find them is worth 1 mark, okay? Maybe a half. Again, it depends on what the question's out of and whether I need it all to add up to a whole number. So sometimes I'll make things worth 1 and sometimes I'll make them worth a half, just depending on where we're at. And then finally, all we're going to do is we're going to take our values and plug them into KSP. So KSP, I'm rewriting things here way more than you would need to. Ag plus times S2 minus. Don't forget to square that. And we get silver is 2.58 times 10 to the negative 17. And sulfide is 1.29 times 10 to the negative 17. And we get oh, and what did I forget? I forgot to square the Ag. So don't forget to square the Ag. And when we do that, we get 8.6 times 10 to the negative 51. Yes? Okay. How do we feel about those? Those are good? Okay. I feel like we could learn another type of problem today as well. Okay, or at least get introduced to it. Okay? Make a passing acquaintance with it and maybe, you know, dig in a little more next week. So we are going to actually go to 3.2D. No, let's go to 3.2C. 3.2C. This is does a precipitate form using Q. And we are not going to watch this video right now. What you can do is if over the weekend you're having trouble with it and you're like, okay, I would actually like to see this illustrated with like the lovely little pictures and everything, then you can go and do this. Yes? But we're going to just keep going. Oh, here we go. These are Q questions. Actually, should we watch the video? Should we? Yes? Okay. Oh, no. I'll leave it for you for the weekend. No, we're not going to. Okay. So in these Q kind of questions, this is just like Q for equilibrium. Yes? When you had Q at equilibrium, what were you using it to do? Find the direction of the shift, yes? So if we have a solubility equilibrium, have we all found the page that we're on? Yes? Okay. If we have a solubility equilibrium, AB solid in equilibrium with A plus aqueous plus B minus aqueous, this is on page 54? 64. Page 64. What you're going to do is you are going to be given some ion concentrations. You're going to be given some ion concentrations. You're going to plug them into your Q, and you're going to say, is Q too big? What happens if Q is too big? It will shift to the reactants. Yes? If Q is too big, it's going to shift left to the reactants. And if it shifts to the reactants, what are we going to form? We're going to form a precipitate. Yes? What if Q is too small? It's going to shift to the right. And if it shifts to the right, will we get a precipitate? No. Basically, I mean, we're not even shifting to the right, because when we mix these two things, there's no solid there to start with, because I'm taking one beaker that contains A plus and a different beaker that contains B minus. And I'm going to put them together and I'm going to see, do I get a precipitate forming? Yes? So if I have a big ion concentration, yes, I will get a precipitate forming. If I have a little ion concentration, if it's not big enough, will I get a precipitate? No. Okay, and that's really all there is to it. On the weekend, I'm going to have you watch that video because it does quite a nice job of showing you what's going on. Okay. So, first step is to identify the precipitate. Because in this case, you're actually going to be given two different compounds. This is a mix and match. Yes? But just like those double replacement reactions you did, you're going to say, who is going to be the precipitate? Are you guys pretty good at that now? Figuring out who's going to be the solid in a double replacement reaction? Yeah, so that's all you're doing. Oh my gosh, look, second thing you're going to do, you're going to write the solubility equilibrium equation. Okay, so we're doing it again. Third thing we're going to write the Q expression, which is really the same as the KSP expression. And in fact, if you want to call it KSP and then write a trial in front of it, so if you were to call it KSP equals concentration of A times concentration of B, and you just wrote trial KSP, that also works because trial KSP is another way of saying Q, okay? Oh my gosh, look what we're doing. We're calculating the concentration of the ions, yes? Now, a lot of the time, this is going to be a little bit more complicated because we're mixing two things. What do we have to do to figure out concentrations when we mix two things? What are we doing to each of the substances if we mix them? We are diluting them, okay? So when we mix two things, we're diluting them, so all those dilution calculations that you did in 3.2a, those are gonna come in handy now, okay? If you didn't do the dilution calculations, before you work on anything like this, you should go back and make sure that you've gone through those first, okay? You can use the mole method to do those dilution calculations. You can use M1V1 equals M2V2. I'm going to show you a third method, which is really just M1V1 equals M2V2, but rearranged. I call it the noon method, all right, because the new concentration equals the old concentration times the old volume over the new volume. All right. I personally like it because to me it makes proportional sense. If I quadruple the volume, my fraction here would end up being a quarter. If I double the volume, my fraction here ends up being a half. So if I quadruple the volume, I now have a quarter of the concentration that I did before. If you don't like that, you can just say, Ms. Vance, what are you talking about? Okay, you can stick with one of the other methods. But I'll show it to you, so you get an idea. Oh, look, we're plugging things in and we're solving, yes? And then we just have to go back and say, oh, now I need to compare Q with KSP, which is what we did before when we compared Q with KEQ. And you're going to say, if Q is less than KSP, in other words, it's too small, the ion concentrations are too low, so you're going to get no precipitate. If Q is big, then the ion concentrations are too high, so a precipitate will form. And the chances of you getting the last one are slim to none, okay? But if it just happens to be exactly equal, it means you have just barely saturated your solution. You won't get a precipitate, but if you were to add even just like one more ion, you would get a precipitate. What are the chances of that happening in real life? Like, not. I mention it here because people ask what would happen if they were equal, but it's always going to be either bigger or smaller, okay? Let's try an example. A student wishes to prepare 1 liter of a solution containing 0.15 moles of NaCl and 0.15 moles of lead nitrate. And they were concerned that a precipitate of lead chloride might form. Can they expect that precipitate to form? Well, you need to, because if this was those earlier questions and I said it was 0.2 molar and 0.2 molar, you could just look at page 4 and be done. Are my concentrations 0.2 molar and 0.2 molar? No, they're smaller than that. So you're going to need to use a Q here, okay? Can you please identify the precipitate that will form? This one should be easy. It is PbCl2, okay, PbCl2. Write the solubility equation. Can you do that? Go for it. Can you write the Q? Q is lead ion, Pb, 2 plus, times chloride. Have I missed anything? Pardon me? Honestly, for these ones, I wouldn't even worry about it, okay? Yeah. If you do, though, it's totally fine. Okay, what have I missed, though? Squared, yeah, okay? Now you're going to calculate your ion concentrations, and in this question it's really straightforward. There is no dilution here. You're just told that you have 0.15 moles of NaCl. Can you get away with not writing this? No, I want you to write it down. I want you to say concentration of Na plus is equal to the concentration of NaCl, which is 0.015 moles per 1.0 liters. So we have 0.015 molar. And I actually don't want the concentration of sodium. What do I want? I want the concentration of chloride. I haven't left myself enough room for this, but that's okay. I also want to find the concentration of lead, which is going to be the same as the concentration of lead nitrate, because lead, there's one lead in lead nitrate. So that is 0.15 moles per 1.0 liters. So that is 0.15 molar. I'm rewriting my Q here, but it would be totally fine if you just took these values and then put them up here. Yes? Like you could just put 0.015. I'm just kind of wanting it to be like, this is what you do first, this is what you do second. And if I write it up here, it looks like what we did third, whereas it's what we did sixth. Does that make sense? No? Am I just confusing you? The thing is, you do not need to rewrite Q down here. I am going to so that I can see what I'm doing. But you don't actually have to rewrite it. You could put those values up higher in the question, yes? Okay. This is what I really want. This is why I really wanted to cover this today. Okay? It's a 2-to-1 ratio when I take lead chloride. Why am I writing there? If I take solid lead chloride and I dissolve it in water. Yes? Then I get a 2-to-1 ratio. Is that what I did here? Did I take lead chloride and put it into water? No. What did I do? I took some sodium chloride and I took some lead nitrate. When the chloride is coming from sodium chloride, it does not have to be the same or twice as much as the lead, which is coming from lead nitrate, because they're coming from different places. Does that make sense? So you have to watch out, and this is why I've been harping on about the dump and stir versus the mix and match. And when you dump and stir, like we did for the earlier questions today, you will have that 1-to-2 ratio. But when you are mixing and matching two different compounds, you're not going to have a 1-to-2 ratio. It's going to be whatever number comes out of this. Yes? Does that make sense? Okay. And I will keep harping on this again and again because it is something that people do make mistakes on. People want to, and I will see this a lot, I will see people double this concentration because they're like, oh, there's 2 CLs, I must double it. But if my concentration is 0.015, and it is, right? Concentration of chloride is 0.015, it's not going to be 0.030, because that's just a different number. Okay? And if it's not making sense yet, don't worry. I will harp and harp for the next week or so, okay? I'll just keep going over and over for the next week. So what we had instead of this, so we did not have this. What we did have was we had I'm going to say this is 0.5 liters. Yeah, and then when I put it together, I'm going to get rid of, I'm not going to draw the sodium and the nitrate anymore because I don't care about them. I have 0.015 moles of chloride, and I have 0.15 moles of lead, and my new volume is 1 liter. So can you see why they're not 2 to 1? Because that's how much I put in and it came from here. And this is how much I put in and it came from here. So they are not 1 to 2 because they're coming from different places. Okay, so let's just finish up this one question. All right. So compare Q with KSP and decide if a precipitate will form. Well, we're going to plug in our lead, 0.15, and our chloride, 0.015 squared, and we get 0.15 times 0.015 squared, and we get 2.25 times 10 to the minus 4. Maybe I did that wrong. 0.15 times 0.015 squared equals, yep, I got the wrong number. 3.375 times 10 to the minus 5. Does that sound better? Yeah? Okay, good. Now what do we do with that Q? What do we always do with the Q? We compare it, yes? So we compare the Q and the KSP. So let's go look up our KSP. Well, first we can write Q. Q is 3.4 times 10 to the minus 5. KSP is not given to us in the question. Is there a place you could find the KSP value? Yes, go look in your booklet. What's the value for KSP? Well, if we go to our data booklet and we go to page 5 and we look under lead. Oh, there it is, lead chloride. That's the one we're looking at. It is 1.2 times 10 to the minus 5. Sometimes you'll find KSP given in the question. Other times you will need to go and look it up, okay? Why is it at the beginning again? Ah. There we go. Okay, whew, that was too much work for that. That was 1.2 times 10 to the minus 5. Which of those two is bigger? Q. And if Q is bigger than KSP, we will say, therefore, does a precipitate form? Yes, because it will shift to the left. Because Q is too big, it shifts left, therefore a precipitate forms. So we're going to leave it there. For homework on this one, you're just going to watch the video. So you've been taught this once by me. You're going to be taught it once on the weekend by Mr. Colger. And then we're going to do it again on Monday because this one requires a little more thought process. That first one is pretty easy. This one is quite a bit harder, just in terms of thinking everything through. So your homework, if you have not finished 3.2a, the odd numbers, finish it. 3.2b, yeah, I'm not going to get you to do all the questions. I'm going to get you to do, let's see, 3.2b. I'm going to get you to do numbers 1 through 4. And 3.2c, watch the video and fill in the notes. Okie dokie. Hi. Mm-hmm. Yes. And that's because, where did I put it? Here. Not that one. That's because in that first worksheet, what we were doing is we were actually taking solid lead chloride and we were dumping it into solution. So for every 1 lead chloride we would get 1 lead and 2 chlorides. But here we're not doing that. Here we're taking sodium chloride, which contains 1 chloride for every sodium chloride. So you're going to use the sodium chloride to figure out how many moles. And for the lead nitrate, that's where you get the moles of lead from. And those can be in any ratio you want, right? Because I could take a whole fistful of lead nitrate and put in only a pinch of sodium chloride if I wanted to. Yeah? So that's why it's different. And that's why this is more complicated, and that's why I'm teaching it to you today, and Colger's teaching it on the weekend, and I'm going to do it again on Monday, because it does require a little bit more thinking about. Okay? Yeah. No, it just means that if I say it's a saturated solution, then the concentration is the solubility. Because I could give you the concentration of silver bromide in an unsaturated solution, but that wouldn't be its solubility. Solubility is the maximum amount, and the saturated solution contains the maximum amount.
But it's like the same as
Yeah, here I've just given it to you in moles per liter. That one's in grams per liter. I can either say the concentration of a saturated solution, or I can say the solubility. The two mean exactly the same thing. Yeah, they do. Yeah, yeah.